Welcome to my 8th tutoring session in A-level chemistry. In this video, I'll explain how to write the electronic configuration of elements in the periodic table. The electronic configuration of element describes the distribution of electrons in its atomic orbitals. It is represented using the notation of the periodic table, which indicates the number of electrons in each energy level and subshell. Now let's see how the electrons are distributed in the atomic orbitals of the atom. Now the electrons are distributed around the nucleus of the respective atom. We come across the first shell or the energy level around the nucleus of the respective atom, and within the first shell we will find the subshell with s orbital containing 2 electrons. This is followed by the second shell or energy level. It's also known as the L shell, and within the second shell we will find the subshell with s orbital containing 2 electrons, p orbital containing 6 electrons, and this is followed by the third energy level or the third shell. It's also known as the M shell, and within the third shell you will find the subshell with s orbital containing 2 electrons, p orbital containing 6 electrons, and d orbital containing 10 electrons. And this is followed by the fourth energy level or shell, is also known as the N shell. And within the fourth shell, you will find the subshell with s orbital containing 2 electrons, p orbital containing 6 electrons, d orbital containing 10 electrons, and f orbital containing 14 electrons. So this is how the electrons are distributed or arranged in the atomic orbitals of the respective atom. And the energy levels together are called as shells, and the atomic orbitals in which the electrons are arranged or distributed are called as subshells or atomic orbitals of atoms. Now, how to write the electronic configuration of an element in the periodic table? Now, here is a simplified and condensed version of the modern periodic table of elements. Now, in the periodic table, you will find that the elements are organized in rows called periods. And the elements are organized in columns called groups. Now, the electronic configuration of sodium is written as 1s2, 2s2, 2p6, 3s1, or it can also be represented by a shorthand notation, that is 2, 8, 1, or you can mention the symbol of the inert gas neon within the square brackets, followed by the valence electron in the third energy level as 3s1. Now, in the periodic table of elements, one can find the element of interest by these 4 details. So one can find the element in the periodic table based on its atomic number, or you can find the element by its symbol, by its name, or even by its atomic weight. So symbol and name are the simplest way of finding the element in the periodic table, rather than finding the element using the atomic number or the atomic weight. Now, how to write the electronic configuration of an element in the periodic table? Now, the first step is to identify the element in the periodic table. Now, the element that we have identified is sodium. And sodium, which is highlighted here in the periodic table, it is the 11th element in the periodic table. And that is why you can find the number 11 that is being superscripted preceding the symbol Na. And why sodium is the 11th element in the periodic table? Because its atomic number is 11. And why its atomic number is 11? Because it contains 11 protons in its nucleus. And therefore, there should be 11 electrons arranged around the nucleus of the sodium element. Now the task at hand is to arrange or distribute these 11 electrons around the nucleus of sodium atom. Now the sodium has 3 shells in which 11 electrons are arranged around the nucleus. Now the first shell of the sodium atom, it has 2 electrons housed in the s orbital. This is followed by the second energy level, in which 2 electrons are housed in the s orbital and 6 electrons are housed in the p orbitals. And this is followed by the third energy level, which is the highest energy level in case of sodium atom. And this will be the valence shell. And in the third shell, you find only 1 electron is housed in the s orbital, while the p and the d orbital are unfilled. Now the electronic configuration of sodium is written as 1s2, 2s2, 2p6, 3s1, which explains the distribution of electrons in the respective atomic orbitals. Or it can also be represented as 2, 8, 1, which indicates that 2 electrons are distributed in the first energy level, 8 electrons are arranged in the second shell, and 1 electron is arranged in the third shell. Or it can also be mentioned by a shorthand notation, where the symbol of the inert gas neon is mentioned within the square brackets, followed by the valence electron in the s orbital of the third energy level as 3s1. Now sodium has 3 shells in which 11 electrons are arranged around the nucleus. Now the electrons in the first shell, they are at a lower energy level. The electrons in the second shell, they are a slightly higher energy level, that is in second energy level, while the electrons in the third shell, they are at the highest energy level, also called as the valence shell, where you find only 1 electron housed in the s orbital, while the p and d orbitals are empty. Now let's begin with the nucleus of the sodium atom, which contains 11 protons that are positively charged. Now the electrons in the first shell are at a lower energy level. And why they are at the lower energy level? The reason being, the electrons are closer to the nucleus, and the electrons in the first energy level, they experience a stronger attractive force towards the positively charged protons present in the nucleus. Whereas the electrons in the third shell, they are at a higher energy level, because the electrons in the third shell, they are far from the nucleus and they experience a weaker attractive force towards the positively charged protons in the nucleus. Now this is where the Aufbau principle comes into picture. Now what does the Aufbau principle state? The Aufbau principle states that electrons fill the lowest energy orbitals first before occupying the higher energy orbitals. It follows the sequence of increasing energy levels and sublevels as defined by the periodic table. Now, for example, let's consider the electronic configuration of sodium, which has 11 electrons. The electronic configuration of sodium is 1s2, 2s2, 2p6, 3s1. Now, according to the Aufbau principle, the 1s orbital is filled first because it is at a low energy level. This is followed by the 2s orbital, 2p orbitals, and then the 3s orbital because the 3s orbital is at a higher energy level. And therefore, the electronic configuration of sodium is 1s2, 2s2, 2p6, 3s1, or 2, 8, 1, or it can also be represented by a shorthand notation where you mention the inert gas neon within the square brackets followed by the valence electron in the s orbital of the third energy level as 3s1. Now these are the three different ways of representing the electronic configuration of sodium. Now the first way of representing the electronic configuration of sodium is mentioning the electrons in their respective atomic orbitals. So this notation indicates that sodium has 2 electrons in the 1s orbital, 2 electrons in the 2s orbital, 6 electrons in the 2p orbital, and 1 electron in the 3s orbital. Now the electrons in the first energy level, that is housed in the s orbital with 2 electrons, it is mentioned as 1s2. The electrons in the second energy level is mentioned as 2s2 and 2p6, while the electron in the third energy level is mentioned as 3s1, and together the electronic configuration is mentioned as 1s2, 2s2, 2p6, 3s1. Now coming to the shorthand representation of the electronic configuration of sodium, that is 2, 8, 1 or 2-8-1. Now what does this notation refer to? Now this notation 2, 8, 1 or 2-8-1 indicates sodium as 2 electrons in the first energy level or the first shell, 8 electrons in the second energy level or the second shell, and 1 electron in the third energy level or the third shell. And together the shorthand notation will be 2, 8, 1 or 2-8-1. Now in this way of representation, we simply consider the number of electrons present in that particular shell or energy level. Now there's one more shorthand method of representing the electronic configuration of sodium, where we consider the electronic configuration of inert gas. In this case, it will be neon. And this is how you represent the electronic configuration of sodium, where you mention the symbol of the inert gas neon within the square brackets, followed by 3s1, which mentions the valence electron present in the s orbital in the third energy level. Now 1s2, 2s2, 2p6 is the electronic configuration of noble gas neon, and all that you need to do is mention the symbol of the neon gas within square brackets, followed by 3s1, which is nothing but the leftover valence electron in the third energy level present in the s orbital. Now the electronic configuration is typically written as sequence of numbers and letters. Now the numbers represent the principal quantum number or the shell, and the letters represent the subshell S, P, D and F. The superscript numbers denote the number of electrons in each subshell. Now let us try and understand the meaning of this 3s1 notation in the shorthand representation for the electronic configuration of sodium. Now the number 3, it represents the shell number or the energy level. The letter S, it represents the type of subshell orbital, and the superscripted number 1, it represents the number of electrons in the orbital, that is in the s orbital of the third energy level. Now let's visualize this with the help of a diagram. We start with the nucleus of the atom. Now around the nucleus you find the first energy level or the K shell, where you find 2 electrons housed in the s orbital. This is followed by the second energy level or the L shell, where you find 2 electrons housed in the s orbital and 6 electrons housed in the p orbital. And this is followed by the third energy level, which is the highest energy level in case of sodium. And this is the valence shell, where you find only 1 electron housed in the s orbital, while the p and d orbitals are unfilled. Now, in case of sodium, the shell number will be 3, where you find the valence electron housed in the s orbital, and you find only 1 electron in the s orbital in the third energy level, and that is represented as 1, which is superscripted after the letter S. Now the electronic configuration is typically written as a sequence of numbers and letters. The numbers, as I already mentioned, represent the principal quantum number or the shell or the energy level, and the letters represent the subshell S, P, D and F, and the superscripted number, here in this case 1, denote the number of electrons in the each subshell. Here in case of sodium, it is only 1 valence electron that is housed in the s orbital present in the third shell or the energy level. Now let us consider an example of an element with a higher atomic number. Iron in this case with atomic number 26. Now iron with atomic number 26 will have 26 electrons distributed or arranged around the nucleus, and the full electronic configuration of iron will be 1s2, 2s2, 2p6, 3s2, 3p6, 3d6, 4s2. Now we can divide this lengthy full electronic configuration into 2 parts. Now the shorthand electronic configuration of iron will be written as the symbol of argon mentioned within square brackets, followed by 3d6 4s2. Now this is because 1s2 2s2 2p6 3s2 3p6 is the electronic configuration of noble gas argon. So in case of elements with higher atomic number, the total electronic configuration will be lengthy, and to avoid this, you can use the previous noble gas electronic configuration to abbreviate the configuration. Now we are abbreviated the configuration using the noble gas argon, where we have mentioned the noble gas argon symbol within the square brackets, and thereby we have simplified the lengthy electronic configuration of iron. And finally, we end up with the shorthand electronic configuration of iron. Now, finally, what is the importance of electronic configurations? Now, the electronic configuration, it provides information about the arrangement of electrons in an atom, that is valency of an element. For example, the valency of sodium is 1 because it can lose only one electron to attain the stable electronic configuration of inert gas neon. Now, secondly, it is essential for understanding the chemical behavior and properties of elements. That is to say, elements with similar electronic configuration have similar chemical properties. For example, group 1 elements like lithium, sodium, potassium, and rubidium have similar chemical properties because of their similarity in electronic configuration, particularly the valence shell. And finally, it also helps to determine the valence electrons of atoms. It predicts the formation of chemical bonds, the reactivity of elements, and their placement in the periodic table based on similar electronic configurations. That is categorizing or grouping elements as S, P, D, and F block elements. And this depending on the types of orbital that is being filled. For example, 1s2, 2s2, 2p6, 3s1 is the notation used to describe the electronic configuration of sodium, and it belongs to the S block. 1s2, 2s2, 2p6, 3s2, 3p5 is the notation used to describe the electronic configuration of fluorine, and fluorine is the P block element. And 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6 is the notation used to describe the electronic configuration for iron, and it is the D block element. Thank you so much for watching my video. Hope you enjoyed it, and I'll meet you in my next interesting tutoring session.